Okay, so 2.6, which feels like we're going way backwards, and we kind of are, but I wanted to save this until the end because rational functions are used heavily in calculus, and the function knowledge is very important. So I want to do that as close to calculus as possible. So here we are. Okay. Rational functions, just like rational numbers, are numbers that can be expressed as a fraction. So you've got r of x, a rational function, equals f of x divided by g of x. So some expression in the numerator and some expression in the denominator. We're talking about polynomial type expressions, where f and g are polynomial functions, and g of x is not equal to 0 is a rational function. Now, g of x, obviously, if it's a polynomial, can equal 0. It's just that the function would not exist there, right? And so what we're going to explore today is in multiple videos, because I already videoed this whole lesson, but in realizing, I don't know if it's because I'm trying to use a different microphone or something, but it got way off track as far as like video versus audio. So I'm redoing it. Have fun. Okay, so it'll be multiple videos. And the domain of a rational function is a set of all real numbers excluding the zeros of the denominator. So when the denominator equals 0, then that is where the function does not exist. And we have different types of things that can be going on. So we'll talk about those as we explore. Okay, here we go. So let's talk about 1 over x, the basic rational or reciprocal function. So write down rational reciprocal function. So some people call it the rational function, but you can also see it as the reciprocal function. Okay, f of x equals 1 over x, and let's kind of explore what's happening. So what I want to do is draw an x and a y, and let's go out 4 on each axis. Okay, so if I were to plug in, you know what, I'm actually going to, you don't need to do this, I'm going to do something right quick. I'm going to space it out and give myself more room. And then 1, 2, 3, 4, that was not very even. So basically every other hash mark is, well, or I guess I could say my scale is a half. I don't know why that took me so long to think about. Okay. So if I were to plot points for this graph, or for this function, 1 over x, if I were to plug in, let's say, x equals 0, well, that's a big issue, right? So if I plug in x equals 0, I get 1 divided by 0, which is undefined, so we're just going to leave that, and we're going to come back to it. Let's plug in 1. If I plug in 1, I get 1 divided by 1, that is 1. If I plug in 2, I get 1 half. If I plug in 3, I get 1/3. So somewhere in here. And if I plug in 4, I get 1/4. Right? So it's pretty clear what's happening on the right-hand side. The further this goes out, the smaller this is going to get, and that makes sense. 1 divided by an increasingly large number is increasingly small. So the further this goes, the smaller this gets. 1 divided by 100 is 1/100th, right? 1 divided by a billion, 1 divided by a trillion. It's just going to get smaller and smaller and smaller. Does it ever reach 0? No, because you're always dividing by something. It's just numerically, it never reaches 0. But for all intents and purposes, yes, it does. Let's talk about 1/2. If I were to plug in 1/2, however, 1 divided by 1/2. Well, dividing by a fraction, you multiply by the reciprocal, 2 over 1, and you get 2. Okay, so at 1/2, we're actually at 2. And then if you were to plug in, say, a fourth, 1 divided by 1/4, that would be 4. So if I plug in 1/4, that would be all the way up here at 4. And let's go a little extreme. If I were to go into 1/100th, right? So 0.01, close to 0. That would be 100. So it's just going to get larger and larger and larger the closer I get to 0, which means the graph actually has both a vertical and a horizontal asymptote. So it's approaching infinity as you approach 0, and it's approaching 0 as you approach infinity. So we end up with both a vertical and a horizontal asymptote. We're mainly going to focus on vertical asymptotes and such domain today, and we'll talk horizontal asymptotes tomorrow. Okay. As far as the left-hand side, if I were plugging -1, 1 divided by -1 is -1. 1 divided by -2 is -1/2. 1 divided by -3 is -1/3. And then -1/4. And if I were to plug in -1/2, 1 divided by -1/2 would be -2. So multiply by the reciprocal. And so it would do the same thing, only in the negative direction, right? So at -1/4, it would be -4. So we have this situation. Now this is called, or this has odd symmetry. I don't know if you remember even versus odd symmetry. Y equals x squared is an even function because it has y-axis symmetry. If you rotate it, or if you reflect it over the y-axis, you would get the same thing. However, y equals x cubed is an odd function because it has 180-degree rotational symmetry. If I rotate this 180 degrees, it would land on itself. So even versus odd. So rational functions have odd symmetry. Most basic. They're not always like exactly. They're not always symmetrical, but this one is. Okay. Now, let's go ahead and describe, you know, what was happening. We do have a vertical asymptote at where I wrote that at x equals 0. So at x equals 0, the function is a vertical asymptote. The function on the right-hand side is approaching positive infinity, and the left is approaching negative infinity. And we can actually describe that with some limits. So the limit as x approaches 0, so the vertical asymptote. From the right, though, so from the right, which means you put a superscript plus sign, of the function f of x, or you could say of 1 over x, equals positive infinity. So as x approaches 0 from the right, as we approach 0 from the right, the function is going up to positive infinity. Whereas down here, if we say the limit as x approaches 0 from the left, so that's a little negative sign, superscript, of f of x, we would say that that's negative infinity. Because as x approaches 0 from the left, the function is going to negative infinity. So vertical asymptotes have behavior on either side. Sometimes they're the same, sometimes they're different. We'll talk about that later. But in this case, we can say that. We also have in behavior limits, right? We have a limit as x approaches positive infinity. As x approaches positive infinity, the function is approaching 0. And as x approaches negative infinity, the function is approaching negative infinity. Wow, 0. But from the negative side. So as x approaches negative infinity, the function is approaching 0. From below, 0 from above doesn't really matter. Either way, it's 0, right? So that's because we have a horizontal asymptote at y equals 0. And that describes behavior on both ends, not just one end like with exponential functions. Exponential functions, you know, have that exponential growth, so you have the horizontal asymptote, but it only describes behavior on one side versus the other. And reciprocal functions, it could be both sides. It could have different horizontal asymptotes. We'll have to talk about that later, but yeah. Anyway, so that's your basic rational function. As far as domain goes, remember that domain is all the values for which, all the x values for which the function exists, right? So every x value can be plugged in here and get a value except x equals 0. So we would say negative infinity is 0, not including 0. Pick back up and go to infinity. And then the range, well, the y values, every y value is accounted for except y equals 0. So the same thing, if we wanted to use other notation, we could say all real numbers x not equal to 0, or we could say all real numbers y not equal to 0. Okay, let's talk about this. If I gave you this function, 1 over x plus 4. Now, it's harder to see it in a situation like this, but like if I told you, let's go back, you know, to first semester last year. If I said f of x equals the square root of x, you would say, okay, square root of x looks like that. Hopefully you remember that. If I were to say f of x equals the square root of x plus 4, then that means, oh, shift it to the left, 4. And there we go. Well, this is the same thing, 1 over x, and if I add 4 to the interior of the function, which is where the x is, the denominator, then that just shifts it to the left 4. So it makes sense that I would have a vertical asymptote at negative 4. And let's explore the values around it just to prove that everything is as it should be. 1, 2, 3, 4. So if I were to plug in negative 3, negative 3, plug it in, when I get 1, 1 divided by 1 is 1. So it'd be right here. At negative 2, I would get positive 1/2. And at 0, I would get 1/4. Oh, yeah, there we go. And at, let's say, negative 3.5, right? Negative 3.5 plus 4, that would be 1 divided by positive 1/2. That's 2. So it's mimicking the same thing as what happened up here. It's just shifted it over. So this would be this side, and this again would be over here. So at negative 5, it would be at negative 1. And then negative 4.5, it would be negative 2. And then it would be negative 1/2. So we get this situation again. Okay? So as far as domain goes, which is all I'm really going to concern myself with, it would be all real numbers except negative 4, where the denominator equals 0. And that's because we have a vertical asymptote at x equals negative 4. Okay. Ouch. Okay, I'm going to go ahead and end the video and just pick back up because I don't want to get the sound and visual off. Okay.